All right, you brainiacs, strap yourselves in for this shit. We're diving deep into some hardcore math today. Group action. It's going to be a wild fucking ride. We're going to break down this Wikipedia article for you. And trust me, it's going to be as painless as possible.
It's like a mathematical orgy, groups getting it on with sets, but instead of babies, they're making transformations.
Okay, so what the hell is a group action anyway? Is it as kinky as it sounds?
Well, imagine you got this gang of graffiti artists, right? They're all about tagging their turf, marking their territory all over the city.
So we talk about mathematical thugs messing with the city, rearranging its elements.
Exactly. It's about how a group manipulates a set, moving stuff around, like pawns in some fucked up chess game.
Speaking of moving shit around, let's talk about left and right actions. What's the difference here? Is this some political bullshit or what?
Nah, man, this ain't about left-wing or right-wing crap. It's all about the order you do things in.
So like mixing a Molotov cocktail, get the order wrong and you're fucked.
Damn right. In a left action, you apply the group elements in order first one, then the second. With a right action, you flip that shit. It's all about which side you're hitting the set element from.
Okay, so order matters.
Got it.
Got it. Now let's talk about those notable properties of actions. Sounds kind of fancy. What the hell makes an action notable in this mathematical gangbang?
First up, you got faithful actions. These are the actions that leave a real mark, no bullshit. It's like getting a tattoo that actually looks like something, not some drunken scribble.
So a group action with a purpose,
Yeah.
not just some random shit.
Exactly. A faithful action means that each element in the group creates a unique transformation of the set. There's no redundancy. Each one's got its own distinct way of screwing with the set.
No posers allowed.
Gotcha.
What else we got?
Next up, we got free actions. Think of it like a no two-timing rule. Each element of the set gets hit by just one unique group element. No overlaps.
So it's like a one-night stand. Every element gets a unique partner. No swap and spit here.
Exactly. No two group elements are allowed to have the same effect on a set element. Everyone gets their own piece of the action.
Sounds fair. What about transitive actions? What makes these fuckers special?
Imagine you got this badass drug lord, right? He's got connections everywhere, can get his product from one corner of the city to another without breaking a sweat. That's transitive action.
So, like a well-connected network.
Yeah,
You can reach any point from any other point.
you got it. If you want to move from one spot in the set to another, there's a group element that can take you there. It's all about reach.
Okay, so transitive actions are all about connections. Now let's move on to some really mind-bending shit. Orbits and stabilizers. It sounds heavy.
It is, but stick with me. Let's go back to our graffiti gang. Imagine their territory, their stomping grounds, all the places they've tagged. That's their orbit. All the points they can reach with their actions.
So their sphere of influence, the places they've marked as theirs.
Exactly. It's all the possible outcomes you get by applying group elements to a starting point. Think of it as the gang's canvas for their artistic mayhem.
All right, so what about these stabilizers? Are these like the gang's muscle keeping things in check?
Think of them more like the lookouts. They stay put while the rest of the gang is out tagging, making sure nobody messes with their turf. The stabilizer of an element is the set of group elements that leave that element unchanged.
So they're like the silent guardians keeping things from getting too chaotic.
Damn right. They hold down the fort while the rest of the gang is out painting the town red, or whatever the hell color they're using.
All right, we got our gang, their territory, their lookouts. What else is there to this mathematical gang war?
Now hold on to your asses, because here comes the orbit stabilizer theorem. This bad boy tells us how the size of an orbit, the size of its stabilizer, and the size of the group are all related.
Wait, so you're telling me we can actually measure the size of this mathematical clusterfuck?
You bet. It's like knowing how many members are in the gang, how big their territory is, and how many lookouts they need to keep shit under control. This theorem connects those numbers in a pretty mind-blown way.
Damn, this theorem sounds like some powerful shit. Can you give me a concrete example of how this works?
Imagine our gang has 10 members. They each tag one building per night, but they need one lookout for every 2 buildings they tag. The orbit stabilizer theorem tells us they can tag 5 buildings and cover a 10-building territory with those 10 members.
Holy shit, that's some strategic level thinking.
It is. Now prepare to have your minds blown, because we're about to dive into some examples.
Get me with it. I'm ready for more of this mathematical madness. What kind of real-world shenanigans can we connect this to?
Ever thought about how symmetries of objects can be seen as group actions? Think about a simple square. You can rotate it, flip it, and it still looks the same. Those are symmetries.
Yeah, but how the hell does that tie into this whole group action thing? It's not like the squares are going out and tagging buildings.
Hold your horses. Imagine each corner of the square is numbered. When you rotate or flip the square, you're changing the order of those numbers, right?
Yeah, but what's the big deal?
Think about it. The group is all the ways you can rotate and flip that square. The set is the corners of the square, and the action is how those rotations and flips change the order of the corners.
So the square is our city. The rotations and flips are our gang. And the corners are like the buildings they're tagging.
You got it. And this isn't just about squares. We can apply this to more complex objects, like a Rubik's Cube. The group is all the possible twists and turns you can do. The set is all the colored squares, and the action is how those twists and turns mix up the colors.
Hold on, so every time I scramble a Rubik's Cube, I'm actually performing group actions. I never realized I was such a math whiz. But what about things that aren't, shapes?
Think about shuffling a deck of cards. That's a permutation, right? You're changing the order of the cards.
Yeah, but how is that a group action? It's not like I'm rotating or flipping the cards.
Think about it. The group is all the possible ways you can shuffle the deck. The set is the deck of cards itself, and the action is how those shuffles change the order of the cards.
Okay, so the group is like the set of possible actions. The set is the thing being acted upon, and the action is the process itself. I think I'm starting to see the pattern here.
You got it. And the beauty of it is that we can apply this framework to so many different things. We've talked about squares, Rubik's Cubes, and even decks of cards. But trust me, this shit goes way deeper than that.
All right, lay it on me. What other mind-blowing examples are you hiding up your sleeve?
Let's talk about something completely different. Ever heard of Galot theory?
Vaguely. It rings a bell from some college math class I probably slept through. Something about polynomials and fields, right? Not exactly like party conversation.
You're on the right track. It's a way to study the solutions to polynomial equations using groups. And you guessed it, group actions played a key role in this.
Hold on, so we're going from shuffling cards to solving equations. How the hell does that even work? It's like comparing apples and oranges.
It's a bit complicated, but stick with me. The group is the Galois group of the polynomial, which is a set of permutations of the roots of the polynomial. The set is the field extension containing those roots, and the action is how the Galois group shuffles those roots around.
All right, my brain's starting to hurt a little. So we're basically using group actions to understand how the solutions to a polynomial equation are related to each other.
Exactly. And get this crazy abstract mathematical tool can tell us whether a polynomial equation can be solved using radicals or not.
Wait, so group actions can tell us if we can find a nice, clean solution to an equation, or if we're stuck with some ugly, irrational crap.
You got it. It all depends on how the Galois group acts on the roots. If the action is nice, then we're golden. But if it's nasty, we're screwed.
Damn, that's pretty powerful.
Yeah.
So from shuffling cards to solving equations, group actions are like the puppet master behind the scenes, pulling the strings of the mathematical universe.
You're goddamn right. And we've only scratched the surface. There's a whole universe of applications out there waiting to be explored. But for now, let's give our listeners a chance to digest all this mind-blowing math.
Sounds good. We'll be back with part 2 to wrap things up and leave you with some final thoughts to chew on. Until then, keep those brains buzzing.
Welcome back, you math-hungry bastards. Ready for another round of our deep dive into group action.
Hell yeah. My brain's still sizzling from all that Galois theory crap. It's insane how this abstract math shit is lurking behind so much of what we do.
It's like the universe is playing a cosmic joke on us, using group actions to orchestrate everything. But enough with the philosophical bullshit. Let's get back to the nitty-gritty. Remember those examples we were talking about? How symmetries and group actions are like two peas in a pod.
Yeah, you were about to blow our minds with how these mathematical thugs operate in the real world.
Right on. Let's start with something simple, like a goddamn square. Think about all the ways you can rotate and flip it so it still looks the same.
Okay, so like rotating it 90 degrees, flipping it vertically or horizontally, that kind of stuff.
Exactly. Those are your symmetry operations. Now imagine each corner of the square has a number. When you apply one of those symmetry operations, the numbers get shuffled around.
Yeah, like if you rotate it 90 degrees, the corner that was number 1 becomes number 4, and so on.
Boom. That's a group action in action. The group is all the possible symmetry operations. The set is the corners of the square, and the action is how those symmetry operations mess with the order of the corners.
So it's like our graffiti gang is back, but instead of tagging buildings, they're rearranging the corners of a square.
You got it. Now let's crank it up a notch. Imagine a more complex object like a goddamn Rubik's Cube. The group is all the possible twists and turns you can do. The set is all those little colored squares. And the action is how those twists and turns mix up the colors.
Holy shit, so every time I scramble a Rubik's Cube, I'm basically playing with group actions. I never realized I was such a mathematical gangster.
You're a natural, my friend. And the crazy part is that this applies to way more than just geometric shapes. Think about permutations, like rearranging the order of things.
Permutations? How the hell does that fit into all of this? It's not like we're rotating or flipping things around.
Think about a deck of cards. Shuffling that deck is a permutation, right? You're changing the order of the cards.
Yeah, but how is that a group action? It's not like I'm applying some geometric transformation to the cards.
Think about it. The group is all the possible ways you can shuffle that deck. The set is the deck of cards itself, and the action is the shuffling, how it rearranges those cards.
Okay, I'm starting to see the pattern here. The group is like the set of possible actions you can perform. The set is the thing you're messing with, and the action is the process of messing with it.
Damn right, you're catching on fast. And the beauty of this framework is that it can be applied to so many different things. We've talked about squares, Rubik's cubes, and decks of cards, but this shit goes way deeper than that.
All right, hit me with it. What other mind-blowing examples do you have up your sleeve? I'm ready to have my reality shattered.
Let's talk about something completely different. Glow theory, ever heard of it?
Vaguely. It rings a bell from some college math class I probably slept through. Something about polynomials and fields, right? Not exactly light party conversation.
You're on the right track. Basically, it's a way to study solutions to polynomial equations using groups. And guess what? Group actions play a key role in all of this.
Hold up, so we're going from shuffling cards to solving equations. How the hell does that even work? It's like comparing apples and oranges.
It's a bit complicated, but stick with me. The group is the Galois group of the polynomial, which is a set of permutations of the roots of the polynomial. The set is the field extension contained in those roots, and the action is how the Galois group shuffles those roots around.
All right, my brain's starting to hurt a little. So we're basically using group actions to understand how the solutions to a polynomial equation are related to each other.
Exactly. And get this crazy abstract mathematical tool can tell us whether a polynomial equation can be solved using radicals or not.
Wait, so group actions can tell us if we can find a nice clean solution to an equation, or if we're stuck with some ugly irrational crap.
You got it. It all depends on how the Galois group acts on the roots. If the action is nice, then we're golden. But if it's nasty, we're screwed.
Damn, that's pretty powerful. So from shuffling cards to solving equations, group actions are like the puppet master behind the scenes, pulling the strings of the mathematical universe.
You're goddamn right. And we've only scratched the surface. There's a whole universe of applications out there, waiting to be explored. But for now, let's give our listeners a chance to digest all this mind-blowing math. We'll be back with part 3 to wrap things up and leave you with some final thoughts to chew on.
All right, you math degenerates. We're back for the final round of our deep dive into group action. My brain's still throbbing from all this symmetry and Galois theory shit, but I'm ready for the grand finale. Let's blow this motherfucker wide open.
Hold on to your hats, because we're about to go full cosmic on this bitch. We've seen how group actions show up in geometry with all those transformations and symmetries. We've seen how they mess around with algebra and permutations and Galois theory. But this shit goes way beyond that.
All right, I'm all ears. What other crazy applications are we missing? Hit me with the mind-blowing shit.
Let's talk about physics, baby. Specifically particle physics. You know how those physicists are always chasing after those fundamental building blocks of the universe? Those quarks and leptons and all that crazy shit.
Yeah, the stuff that makes up everything around us. Pretty important stuff, I guess.
Damn right it is. And guess what? Group actions play a crucial role in understanding and classifying these particles.
Wait, so you're telling me that these abstract mathematical concepts are helping us understand the very fabric of reality? That's some next-level shit.
It's like the universe is playing a game of cosmic hide-and-seek, and group actions are the clues that help us uncover those hidden pieces.
Okay, break it down for me. How do group actions fit into this particle zoo?
Think of it this way. Each particle has certain properties, like its charge, spin, and mass. Physicists group these particles based on their properties, and the way these groups interact is governed by, you guessed it, group actions.
So it's like each type of particle has its own little gang. And the way these gangs interact is dictated by the rules of group action. It's all starting to sound like a cosmic turf war.
You're catching on fast. And get this mathematical framework has actually led to predictions of new particles, some of which have been discovered later on.
Damn, that's some powerful shit. So it's not just about understanding what we already know. It's about predicting new, undiscovered stuff.
Yeah.
That's some next-level science fiction shit right there.
It's like using math to unlock the secrets of the universe one group action at a time. And this is just one example. Group actions pop up everywhere in physics, from cosmology to quantum mechanics. It's this hidden language that connects seemingly disparate areas of physics.
All right. I'm convinced group actions are the fucking bomb. But before we wrap up this mathematical mindfuck, what's one final juicy tidbit you can leave our listeners with? Something to really make their brains explode.
Think about the symmetries of space-time itself. Einstein's theory of relativity tells us that space-time isn't static. It can be warped and curved by gravity. And guess what? The symmetries of this curved space-time can be described using, you guessed it, group actions.
Hold on. Are you saying that the way gravity bends reality is governed by group actions? That's some heavy shit, man.
You got it. The group in this case is the set of all transformations that preserve the geometry of space-time, and the action is how those transformations affect the points in space-time.
Damn, that's some deep shit. So from the smallest particles to the fabric of the universe, group actions are pulling the strings, making shit happen. It's like a cosmic conspiracy.
It's like this universal language of symmetry and transformation. That underlies so much of what we observe in the world, from the spin of an electron to the expansion of the universe.
Well, there you have it, folks. We've journeyed through the wild world of group action, from shuffling cards to bending space-time. I hope you're as mind-blown as I am.
Keep those brains buzzing, and remember, math isn't just some dry subject you slept through in school. It's the key to understanding the universe, one crazy concept at a time.
And that's a wrap for our deep dive into group actions. Until next time, stay curious. Keep exploring. And don't be afraid to get your hands dirty with some mind-bending math. We'll catch you on the next deep dive.